So this is the instruction set for the, what they call the brain. I can't remember what the brain is. It's an acronym. But this is the instruction set for this programming language. This is an offline, so the He robot is programmed offline. And it uses what we call a script language, which is basically a text language, which is what all these robots over here use. They use a script language. But what's nice about these robots is a lot of your commands are in the firmware of the computer. So that means you select command and then it'll pop in the right syntax for you. Now what syntax? We talked about that before. I know we have. What syntax? S-Y-N-T-A-X. So it's not like Alabama's syntax, which is S-I-N-T-A-X, right? Which is what they call their tax on cigarettes and liquor and stuff like that. Well, it's not a language. It's the written language. So syntax is the correct way of writing the language. So when you take English composition and then you turn in a paper, one of the things that they grade, of course, is the syntax, which means do you put the commas right? Do you spell words right? Do you put punctuation where it's supposed to be? Right? You understand that's syntax. So what we do is we come up here, once you click on the start button, which is on your computer on the lower left hand, we call this a taskbar at the bottom. Okay, wait a minute. Okay, so then we click on students, and then when students loads up, there's a bunch of folders out there, and one of them's called robotics. Right? And robotics.
Quick question. What username? Next to? Yeah, I did that.
That's why I came back to help you. Now, once you click on robotics, then there should be a folder in there called manuals. These are the manuals on all the robots in the lab. And then, of course, we're going to play around with the He robot. By the way, if I were to rephrase this, when we were writing the grant for the robot, and Nancy wrote up He robot, they said, well, why can't it be a she? But He stands for Heath Education System. So this robot was originally sold by Heath Education. So this is not a male robot, it's just a mobile robot. This is our mobile robot that you see me driving around. Okay, and then hit He robot, and then you need to go to BrainScript. And this is the instruction set for the Hero robot. So I try to say Hero robot is what I like it. So an instruction set lists the commands that are available in a programming language.
If some of these computers walked out, you only
that one is. Because I use it for I remote into it.
Gotcha. Alright. I was like, is it me?
Well, it is you. You're not retraining.
I I know I pay attention better when
I
I'm
don't-
like
I have to
here,
like it.
this close. If I have this much distance, I don't pay attention.
So basically, this is a standard command set. And the first thing you see is the command. So we don't want keywords. Let's get down to command. The first thing you see is a command. This is not Digitalio. This is Digital IO. A lot of people say Digitalio because that's what it looks like. But this is a Digital IO command. So here we're talking about input-output ports, right? We talked a little bit about what a computer consists of. How we did that in this class, basically what a computer consists of.
This one doesn't work either.
Yeah, it's supposed to.
Thank you.
So what's the parts of a computer?
A monitor? Right?
No, I'm talking about a computer.
With what?
Oh,
What's the part of any computer?
This thing.
a hard drive?
Well, not the hard drive. It's a part of any computer.
It's part or heart?
Well, this is a computer. It don't have a hard.
CPU?
It don't have a hard drive on it. Okay, we got to have something called a processor.
Computer
What does the
processor
processor do? It runs programs. Period. Normally, okay, so that's what the processor does. Where does it run programs from? Where's the programs at that it runs? They're in the memory of the computer. So we gotta have memory, right? Understand? Gotta have memory in the computer. If we didn't have memory, then we couldn't run programs. Everybody understand that? So we gotta have memory. We gotta have a processor. Gotta have memory. We got different types of memory. Thank goodness.
What, long?
So is a USB drive, is that a memory? No. That's mass storage. We're talking about it's inside the computer. When we talk about memory, we're talking about the memory that's inside the computer. But then I'm not inside the computer. So how do I get information inside the computer?
You insert it. Or there.
Well, there's got to be what we call a portal into the machine. And we have two categories of ports. We have input ports and we have output ports. And then we have some ports that are literally bi-directional in their input-output. But over time, all the ports in the computer, whether they're input ports or output ports, have become known as IO.
As what?
As IO ports. I/O.
Abbreviated.
Yeah, but this is not a input command. This is an output command. So digital IO. What we're going to do, so digital ports, we can only do two things with digital ports. We can either turn them on or turn them off. And this gives you a lot of the things. So we can turn them on, we can turn them off, we can say yes, we can say no, we can say true, we can say false, or we can say 0 and 1, which is what we do with binary. 0 and 1 is very, very popular now, even for on-off buttons, where they put a circle and put a dash to the up and down, which stands for 0 and 1, right? So 1 turns it on and the 0 turns it off. So on this port, on this robot, we've got quite a few IO ports that's available to us. A lot of them are not even used, but we could use them if we wanted to. There are two that's available to us. We have two spotlights on the robot. It's got a blue light that comes on. It's got some headlights or white lights that come on. So if I want to turn those on or I want to turn them off in my program, then this is the command we would use. So what we need to do, first of all, most of your computers, everything inside the computer uses a system we call binary, which is ones and zeros. And why do we use ones and zeros? Because we can represent them real easy by electricity. You see it all the time. This is ones and zeros up here on the slide.
So like the matrix.
Kind of like the Matrix. Yeah. Back in the original Star Trek, when and they spoke in binary. So they clicked like that. Really, really funny. Really good.
So if you define binary, like give me a definition.
Binary is a numbering system. But instead, so decimal is a numbering system. In decimal, we have numbers, we have digits available, 0 through 9. Now, the problem is, if I'm going to try to put that into an electronic circuit, that's almost impossible for me to represent. So how would I represent numbers 0 through 9? Electrically.
Is that a question?
Yeah, how could I do that? How could I electrically represent numbers 0 through 9? So I could take a flashlight and I could have different positions on it, right? And each one of them would change a voltage level going to the bulb. And the bulb would get brighter the closer I get to 9. And it would, when I got to 0, it would do what? It would turn off. Then I go across the campus over there, get on that hill over there, and I'm trying to send you a number. What's the odds of you getting that number right? So just looking at a lighting. I guarantee you, almost everybody in the class will come up with a different number. So digital, even though we understand digital very, very easily, it's almost impossible for us to represent it and store it and move it around real accurately. So how many I could go over there up on that hill and I could have a flashlight and I could turn it on or I could turn it off? Everybody should be able to do that. And this has been what they've been using in the Navy for years to communicate with ships. Ship to ship when they don't want to use RF, right? So they use that's a binary code. So binary, and if you understand the decimal numbering system, if you understood the decimal numbering system, you could pick up on any numbering system that's out there. If you understood the decimal numbering system. The problem we have is a lot of people do not understand the decimal numbering system. Because why? Well, you've been using it all your life. Right? You understand? Well, not all your life, probably first grade. But you probably were counting and stuff like that even before you started school.
We all see enough numbers today.
Huh?
We all see enough numbers today.
Yeah. So we can do math on them. We can do all kinds of stuff because we understand that. But as far as me trying to store that information in a computer, that would be basically very, very hard, right? You understand? So the way this works is every number system has a base. And this is the number of combinations that we have available per digit.
8,739.
Wait, we're talking about the base yet. You're looking at the number and I'm talking about the base. So what we have in a decimal numbering system is we have 10 combinations, 0 through what? Through 9 to represent digits. Well, also it tells us in an exponent, it tells us what a number is raised to, right? I'm sorry, it tells us the number and then we have the exponent. So every number system basically goes like this. Power of tens. Of course, we learn them as units, tens, hundreds, and thousands. But this is the true meaning of the base. So any number raised to the 0 power is 1. Then we have 10 to the first, which is 10. Then we have 10 to the second, which is 100. Then we have 10 to the third, which is 1,000.
10 to the 0 is 1. Always. Or
10 to the 0. Any number raised to the 0 power is 1. You could put 1 billion and raise it to the 0 power, and it would come up and be 1. Well, binary, these are the only digits we have in binary. That's it. Zeros and 1. But what's nice about binary, I can represent very easily this with a voltage. So if I got a 1, I might have 5 volts. If I've got a 0, I might have 0 volts. And now I can store it electronically. I can transmit it easily. I can process it. I can do math with it real easy. If you understood binary math, you'd throw base 10 math away, especially addition and subtraction. Because the most you can have, you always carry on the 2. But this represents 2 to the 0. This is 2 to the first, 2 to the second, 2 to the third, 2 to the fourth.
Why is it 2?
Because it's base 2. It's binary. So binary has a base equal to 2. Decimal has a base equal to 10. And the base of an exponent is the number that we raise to some power, right? So decimal is a base 10 system. Binary is a base 2
Where's the
system.
decimal in 8739?
What do you mean the decimal?
Is it period after?
Yeah, 2 to the second. But
Like, normally that's why it's period.
what you mean?
Like, point, da 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 da, or.
Well, any number on this side, if I put the decimal
See, that's-
point, and then I put a 6, this would be 10 to the minus 1. This would be 5. This would be 10 to the minus 2. Over here, this would be 2 to the minus 1, 2 to the minus 2, 2 to the minus
Right.
3. So any base. So base 8, we don't have any number above 8. And this would be what? This would be 8 to the 0. This would be 8 to the first. This would be 8 to the second. This would be 8 to the third. Base 16. So base 8, base 16. These are number systems that we use to represent real large binary.
So the power is always 2 in binary, and the numbers are always 0, 4, 1.
Yes, that's it. But that's what we're saying. Binary means 2, 2, right? Bi means 2. Decimal means 10. Octal means 8. Hexadecimal,
6.
which is, well, hex would be 6, but it's hexadecimal. So hexadecimal is a base 16 system. 6 plus what? Plus 10.
Who came up with that?
It's just number systems. When I was in college, we had to develop a base 36 system. Well, it was no big deal, but it was hard to convert. We use hexadecimal and octal and binary so often that most scientific calculators will convert them for you. But if I needed to go to base 10, then I got to get these 2's into base 10. And so this would be 1, this would be 4, this would be 1, 2, 4, this would be 8, this is 6. So base 2 is real neat because every digit, the decimal weight goes up by 1. Doubles. And then I would just add the digits that's got 1 in them. So that'd be 16 plus 4 plus 1, and that would be the decimal weight of this number. But what's nice about it, if I'm going to turn on a light, or if I'm going to turn off a light, if I'm going to, but now I'm representing it with, I can represent binary real easy because things are either what? On or off. I can transmit it over great distances with very little error. I can store it in memory real easy because I'm only storing 0s and 1s. I can process it real easy. I can add it. I can subtract it. I can divide in binary, which microprocessors can't really do. They appear to do it, but I can do everything in this very, very easily, but as a human, it makes it real hard to understand. But here what we're doing is we're saying, okay, binary or digital. So digital usually means a digital port. That's what a digital port means, is that we can do one of two things. If it's an output port, we can do what? We can either turn it off or turn it on. Or we can either say yes or we can say no. Or we can say true or we can say false, depending on the language. So you just can't go into like a computer over there and say, okay, I want to turn this off. When the language does not recognize off, the syntax says you have to put what? On. So all these robots, if I want to turn a port, we turn it on or off. And that's the only option we got. Now the Heath robot gives us all these options. So basically it's up to you. So when it translates this program over, so we write programs in, so when I originally got into microprocessors, we had to write, our programs were binary programs, which was very, very complicated. Over time, they came up and they say, well, what happens when I can't understand a foreign language? So right now, the president's up there in the United Nations making a speech to all these people from different countries, and a lot of them don't have any idea what he's saying. So what do? They have translators. So that's what we do in computer languages too. So we'll have a binary program called a translator. So we have two. We have an interpreter and compilers. But when I run the program, it goes to the translator, and then the computer, all it sees is what? Binary. And we have two types of translators. We have what we call compilers and interpreters. But we're not going to get into that. But that's what happens. So what it does, it gives me the ability to program that hero robot in English. But the robot itself has no idea what English is. All it knows is ones and zeros. So when we go over there and tell it to run the program, then it runs through a binary program called a translator that translates it over to what? The machine language for the computer.
What did you call those two? You used different words. One was translator, one was a
Well, no, they're both translators. We have two types of translators in computers. We have interpreters. And we have compilers. So a compiler would take a program and develop another machine language program that we run. So we don't run the compiler. An interpreter, what it will do is it'll take one command at a time and translate it one command at a time. So the interpreter, the compiler compiles the whole program. So that would be like me reading a book. So an interpreter would be like me reading a book, and then we have a person that interprets it to your language. A compiler would be like what they've done with the Bible. What have they done with the Bible? They've compiled that. So what they've done is they've completely translated that into a language that we understand. So now you can get the Bible in any language, but originally, the original versions they found was Greek, right, or Latin? Greek.
If you take Spanish and you translate it word for word, it doesn't really make sense once you break it down.
Well, computers it does. Everything's.
So, but if you translate, like, you take the whole paragraph and sort of go, this is how I would say it in English. So that's kind of what you're saying.
Well, it's not. This is the way I would say it. This is when we translate or compile, the translated program has to be perfect. So one of the things the translators look at, is syntax. So if you have the wrong syntax, and we'll see that when y'all do some of your programming over here on the Hero Robot, some of y'all is going to have a syntax error. And when it tries to translate it, it's going to pop up and says, I don't understand, I can't develop the right code because you use the syntax. Now, in spoken languages, syntax does not have to be perfect, but computer languages, syntax has to be perfect. So your high-level language has to have the right syntax so it will be translated correctly. And we call those syntax errors. If you've ever been in programming, you've probably seen a few syntax errors. And that's when your translator tries to translate your high-level program, and it cannot do it. So we okay?
Yes.
So that's a little deeper than we wanted to do, but it's always nice to know.
Always nice to keep educated.
So what we have here, right down here, it says syntax. So digital I/O. So I'm going to use this to turn an output port on or off. So what's nice about computers is they give these ports. These ports are at an address, and the address is binary. And so in the machine, what we call the machine language, which is binary language, I would have to know the physical address of that port. But my phone, and so used to when you call somebody, by George, you had to know their number. Now, how many numbers do you know? Very few, because you do what?
You insert them in a contact.
You give them a name. So now I select a name, and then my phone translates that over to a what? To a number. Thank goodness. Because all the numbers on all the addresses on the internet are binary addresses.
Oh, we always have Rolodex.
Yeah, we are. You used to have a lot of
And
stuff.
phone books. When's the last time you got a
Used to-
phone book delivered to your house?
Usually we get one, but we keep a landline at our house.
Yeah.
So we still have the same phone that we've had for years. So we still get a phone book, but usually it's got, all it is yellow pages. So, okay. So, in this one, what most computers use, instead of using a binary, instead of using a name, some of them give you the ability to give them names, and some of them give you the ability to establish a name. So that's true. That's true with even these computers. So, so these are the ports, but ports are addressed through a what? Through a name. But then every name is assigned a number. These are speeds, by the way.
Is there a projector hanging out right there?
No, that's
What?
it's a Minio, which I used to use when I used to walk all the time.
What is it?
So it's what I'm doing here, where I come up here and mark on the screen with this pen right here. We could do it up there on the board, but I don't get up there. So that's why it's not connected. So what we need to know for our computer is the ports. So we got digital I/O, and then it says we have to define a what? No, right here. Port. So what they do on the Hero robot is all the ports are assigned a decimal number. So the two ports that we're going to use are port 15 and 16. One of them turns on the blue light and one of them turns on the headlights. We'll go over and look at the robot in a minute. So what does it say I need to do? By the way, this is syntax. If you see something in uppercase, most programming languages are not case sensitive. But what you see, if you see something in uppercase letters, it means it has to be spelled exactly the way it is. You cannot misspell it. Everybody understand that? Okay. If you see this pipette right here, it means you make a choice. You're either going to say you're going to do what? You're going to turn it on or you're going to turn it off. And that's pretty standard syntax for most computers. Because they don't know what you're going to do. So if I was going to type this command in, I would start off by typing what? Digital I/O, Digitalia, right? And then what a lot of people say, you see this right here, there's a what? There's a space in there. If you leave that space out, it's a syntax error. And then I would come in and then I would say what? Huh? I would come up here and I would say like 15, and then I would put a comma, and then I would say, and that would be, see what I'm talking about? Yes or no? And then to make sure you understand the syntax, so we don't put parentheses, by the way, that just shows us options. what they do is they give you a bunch of what? EXAM. Give you a bunch of examples to make sure you understand the syntax. So notice there's a space right here, but there is not a space between here, and that gives people problems because normally when you type, you put a space after a comma. Well, if you put a space after the comma here, then you've got the wrong syntax. Right? You understand? So that right there would do what? That would come up here and that would turn on the light. One of the lights. I think that's the blue light. When I ran this program. So that's what we call an instruction. So an instruction consists of a command and then the stuff that we use for a command. Now, if I want to, how long would this stay on? Well, it's going to, if I come up here and do this, how long would it stay on? It's a computer. How long would it stay on?
The battery runs up.
How long would it stay on? You'd never be able to see it because it would be on and off so fast. So what do we need to do? If I'm going to turn something on and turn it off, what do we need to put between those two commands?
Space.
Some type of space don't mean anything. I'm opening it up for another command. We need to put some type of delay in there, right? Does that make sense? So, by the way, the commands that y'all going to use, I put these in yellow. So there's very few commands that you're going to use. So there's a bunch of commands or instructions available to us. So I've got these highlighted in yellow. So I'm not going to move forward. What do you think move forward is going to do? It's going to move the robot forward, right? And then we got very few commands. Rotate clockwise, rotate counterclockwise. You're okay there? What that's going to do? What's that going to do? It's going to turn the robot, right? I know the difference between clockwise and counterclockwise. Say, we'll make the robot say something, and this is the command I'm looking for. It's called what? Sleep. So that's the command on this robot. Every robot's got this. We have I/O ports on these things, and it takes time for a lot of the I/O ports to respond. This will pop up when you take operation in programming. You'll go down there, you'll be stepping your program, and you want to go down there and you want to open the gripper. Well, you have to tell it to open the gripper, right? And the gripper is hooked up to a port. So you're going to say you're going to turn that port on. Well, the gripper would open. Then you say, oh, I'm going to go down and pick up that block. So you stage the robot above the block, you tell it to open the gripper, you come down, then you tell it to close the gripper, then you come up. When you run the program, it comes down, and it comes down and stops for a second, then it starts moving, the gripper don't quite open, it hits the block, and then the gripper opens. Why? Because you got a computer that's running in a nanosecond world, and then you got a hand out there. I had a hatchback car one time, and I had the trunk open, the hatchback open on it, and I had my keys in my hand, and when I started closing the dang thing, my key slipped out of my hand, and I got this level right here, and I watched those keys go all the way down and fall through the hole, and I didn't stop. I still closed the trunk because my brain is real fast. How many times y'all thought about something, but your arms didn't respond fast, right? You understand? Well,
yeah,
that's
like
the
when I see
problem.
my
We got,
phone start to fall and
yeah,
can't grab it
yeah,
fast
but
enough.
see, that's what we got. So you're taking a brain that can process in milliseconds, and you're trying to move muscles that don't move in milliseconds, right? You understand? Well, that same thing's true with the robot. So I tell it to open the gripper, and then I go to the next command, which is the motion command. And the robot says, okay, open the gripper. But what happens is the what? The gripper don't have time to respond. You can single step through the program all day long. You can step it through there and it works perfect. You run it in automatic mode and it collides. Because you didn't deliberately put a what in there. Stop. Well, not a stop. We don't want to stop the robot. We just want it to pause, right? Just delay. So this is the delay command for this robot. Every programming language I've ever seen has a pause.
It's called sleep.
Here they call it sleep. I think Motorman calls it timer. So you put a little timer command in there and you deliberately pause. Yeah, and like I said, it depends on the language. So Spanish, sleep would be a different word, and that's what they would use, right? You understand? So basically, every one of these programming languages on all these robots have a delay command. Because your computer runs programs faster than the mechanics of the robot can respond, right? You understand? So when I say open that gripper, it's got to send a command out to a directional control valve. The directional control valve's got to shift position, which routes air up to the gripper, which goes to a pneumatic cylinder, which opens or closes depending on the flow rate of the fluid. So we tell it to open in our program, and it takes time, and then the robot says, okay, I send that command out, and then what does it do? What does the computer do? It goes to the next command. Unless you tell it to do what? Until you tell it to pause. Not stop, pause. Because we have a stop command too. So usually we got end, stop, those are the same thing. End means your program is over. So that's what we're talking about, just little things like that. So we got to tell it to just do what? Just pause. So the pause command for this robot right here is the sleep command. And it says, okay, what does it say it's going to do? It says it's going to cause a script to pause for a predefined number of milliseconds. So that means, so if I wanted to pause for 1 second, what number would I put in? Huh? I would put 1,000. If I wanted to pause for 5 seconds, if I wanted to pause for 5 milliseconds, you'll never see it. Right? Y'all understand? But it would do that. It would pause for 5 milliseconds. So let's leave it on, and let's leave it on for, so I'd come up here and I'd say sleep. And then I would say 5,000. And that would be 5 milliseconds. And then I would come down here and I'd do the same thing. No, I'll leave it there because I'm turning it off. And then I want to move. So I'm going to come up here. I want the robot to move forward. So I would come up here and do what? Okay. Come on, baby. So the move command, if I use the right syntax, it says what? Move forward, right? Face. Move it. Yeah, let's put 5 feet. But y'all gonna have to use y'all gonna have to do y'all's programs in centimeters. Okay, now what do you want to do? First of all, normally for this robot, anytime you do a commotion command, it's got inertia to it. So normally what we do is we put a little pause in here after each, Usually about 40 milliseconds is enough. And then we'll spin it around. Let's do 180 degrees. And then we'll bring it back. Well, let's go clockwise. So what does it say? It says rotate clockwise, and then it rotates the robot clockwise a predetermined number of what? Degrees. So I type in rotate clockwise, and then we'll do 180 degrees. You don't put degrees out there, which a lot of people do. They'll type in degrees, because it's understood to be degrees, right? You understand that? It's just like this is a. What do you mean?
Why is it known that it's degrees?
because that's what the syntax says it is. So it comes over here, that's what the syntax says it is. So the syntax says rotate so many what? Degrees. So like rotate the robot clockwise a predetermined number of degrees.
The word rotate
Yeah.
really
So
was
it's just like when we said to sleep, it says in milliseconds. How does it know it's in milliseconds? Well, that's the only thing it sees. So if it knows it's degrees, we don't have to put what? Degrees. Does that make sense? Then what we want to do?
Oh,
Well, we want to pause it. Sleep. I almost said pause. About 40 milliseconds, and then we'll move forward 5 minutes. If this is working right, what should the robot do when we run the program? You should see one of the lights turn on. It'll stay on for 5 seconds, then it should go off. After it does that, it should take off forward. Should move forward 5 feet. And when it gets out to 5 feet, it should have a little pause there. And it should do what? Should turn around. Usually, no.
Look forward 5L. I'll just choose it.
Over there it does. It says so. I hit shift on my phone. We usually do these in uppercase. I thought I had capital locks on. Sorry.
So in this case, I guess, you move forward 5 feet and then the rotate 180, put it back where it was.
Spun it all the way around.
So you don't do something backwards.
Yeah, another thing we probably need to do, and y'all are going to do this, is we're not going to run the robot at full speed. So next thing we're going to do is look at the speed command. And these are percentages, by the way. Set both speeds. So we're going to start off by setting the speed at, I think 40 is what we like to use. And there's our program. Now, how do I get this to the robot?